Hi guys, I'm back. Part 2 of 2 for Tuesday's April 28th lecture. I'm still on chapter 10, rotation, and we're going to talk about torques. So, just finished talking about moments of inertia, and we're going to spend some time talking about torque, net torques, and Newton's second law for rotational quantities. So, this letter right here is the Greek letter tau, for like a Greek T for torque. And you'll see that a torque is a vector quantity, and it's actually represented typically by a cross product. This is like a position vector with respect to an axis of rotation, a pointing vector with magnitude of position, and this is an applied force to a rotating object. So again, just like everything else we've been talking about, all objects that we talk about have some kind of volume and length and width and height, not point masses anymore. So I typically start this conversation off just talking about like a wrench. So here's a wrench. And this is typically something we all rotate or have rotated in our life. And, typically our axis of rotation is where the bolt is here inside of the wrench. And so I've marked it with this blue X, the axis of rotation. And depending on an applied force, so if you apply a force like this, for instance, it's lefty-loosey, right? It'll cause a rotation counterclockwise. If you apply a force down like this, then you'll experience a clockwise rotation. And really, we can apply different kind of forces to an object that has the potential to rotate around these axes of rotations, and get a torque or a rotational force. So let me describe a couple different forces that we could apply. Maybe I could apply one here. Maybe I could apply one here. The question is, which one causes a bigger torque? And that has to do with how far away from the axis of rotation you are. And in fact, this force, forgot to label, let's call it F2 and F1 vectors. F2 would cause a greater rotational force. One of the ways I know that is if I tried to apply a force even closer to the axis of rotation, F naught, could that, in the absence of these other two forces, could that force F0 cause a rotation? And the answer is no. We've all tried to apply a force to a wrench that way before, probably, and nothing's happened. And you can notice as you kind of go gradually farther and farther away from the axis of rotation that it becomes easier and easier to rotate or to loosen the bolt effectively. This is picked up in the definition of torque by this R vector. The R vector is how far away from the axis of rotation you are. So the R vector for F sub 0 right here is actually just 0, right? 0, let's call this the x hat, in the x hat direction. R1 looks like this. R1, maybe it's at the halfway point. Let's call this torque has a length L over 2x hat. And R sub 2, R sub 2, kind of getting hard to draw that on here. Let's make it a little bigger. R sub 2 is the full length Lx hat. So I told you this R is like a position vector, and it's defined with respect to the axis of rotation. It's different for each applied force. It's 0 for this force, and it just points to where the force is acting on the body. So here it's L over 2, if that's a midway point for F sub 1. And for F sub 2, again, it points to just where the force is applied. It's the full length in the x hat direction. So you can see that the torque is proportional to kind of that length, and it's telling you that the farther out you go, the bigger the torque is going to be. And that's why you can see some like plumber's wrenches. Oops. Man, those things can be super long. And it's because if they apply a force all the way out here, it's much, much easier because R is so big to get a torque. And of course, the bigger the torque, eventually we'll see that the bigger the angular acceleration. Anyhow. So have you ever tried to apply a force like this to wrench? Ever done this? Apply a force like that to wrench and get it to rotate around this axis of rotation right here? Answer is no. If this is F sub 3, there's still a R vector, right, associated with F sub 3. It points to right here where it's acting, but F sub 3 is parallel to R sub 3, and we know physically that this creates no torque, right? No rotation is another way of saying it. And that has to do with, well, that's the physicalness of it, and then the mathematics part of it has to do with the fact that there's a cross product here. So remember, just like the dot product picks out parallel components and multiplies it, the cross product, remember cross product, or the vector product, picks out perpendicular components and multiplies them. So if there are no perpendicular components between R and F, like this case, then the cross product is 0. Okay. So that's good to know. One way that we can see that is if we did define torque via the determinant. So I feel like you guys, if you haven't seen it already, you'll be seeing it like this week or something. Or I can just write the formula for it. Some of you know the determinant in this form. Looks like this. What I'm doing is I'm just writing out like the x, y, and z components of an R vector. So like generally speaking, an R vector could have like an x component, a y component, and a z component, for instance. And same with a force in Cartesian coordinates. It could have an x, y, and z component, just like the R has an x, y, and z component. The determinant is just a formula for the cross product. So I might have to zoom in here to get it all in. It's x hat ryfz minus rzfy minus y hat rxfz minus rzfx. Out of space, I'm going to go down here, plus z hat rx fy minus ryfx. So for instance, if I used my R3 and F3 above, right? R3 above is just L x hat plus 0 y hat plus 0 z hat. F sub 3, we'll write it as minus F3 x hat, which means it has 0 y hat and 0 z hat. And I would be plugging this into the determinant to find the torque from this quantity. It would look like L00 minus F300. And honestly, the only components that would come out of this is something with an R sub x and an F sub x. So here's an R sub x, an F sub x, an R sub x, and an F sub x, but everything else multiplying it is 0. So I would have 0 minus 0 in the x hat minus y hat L times 0 minus 0 F3 plus z hat L times 0 minus 0 times F3. So the whole thing is just the null vector. So when taking the cross product of these two parallel components, of course, the torque vector will be 0 for this quantity. Okay. So just getting started here, just warming up. We've seen kind of the opposite case here, where F sub 2 has a perpendicular component. I could see that R sub 2 crossed with F sub 2 would give me an actual torque. So let's look at that one really quickly. R sub 2 was equal to L x hat, and let's say that F sub 2 is equal to positive F2 in the y hat. The determinant then, or the torque from these two vectors alone, would look like plugging it into my equation, I would have x hat 0 minus 0 minus y hat L F2 minus 0 plus z hat, oops, just kidding here, y hat would be L times 0 minus 0 plus z hat L times F2 minus 0. So the whole thing would give me a z hat L times F2, or the torque from F2 would be equal to L times F2 in the z hat. So this is a non-zero torque, and if you remember, of course, that's because I applied my force 2 out here, and my L2 or my R2 was perpendicular to that. Here's the axis of rotation. So a torque from F2 gives me a positive value in the z hat direction. And so the resultant vector is in fact out of the board. So this is very similar to when we talked about omega and alpha, in the sense that we talked about clockwise and counterclockwise rotation. So I think it's pretty clear that if I applied a force, it would move this thing clockwise, right? Around in a circle, counterclockwise around in a circle, F2. And that's associated with the positive z hat direction. So the standard notation is that counterclockwise is positive, or the positive z hat direction, and that's the direction of the torque. This makes a lot of sense because eventually when I'm going to talk about the sum of torques, it's going to be proportional to I alpha. Remember, alpha will also be in or out of the page here. So it also leads you to understand that if I had applied a force in the other direction, maybe here's an F sub 4, down like this, you can imagine, here's my R sub 4, with respect to the axis of rotation, that this is going to create a clockwise rotation. We call that negative because this would be in the negative z hat, of course, if this was the positive y, and this was the positive x. Or out of the board, or into the board, sorry, here. Okay, so typically we'll talk about torques being positive or negative if they're counterclockwise versus clockwise. And really that just has to do with the direction of the resultant vector that you can see by taking the determinant or the cross product here, or you can do that by looking at the right-hand rule. So again, if you use that right-hand rule that we were talking about and you line your pinky up with the direction, so here's your fingernail, you line your pinky up with the direction of the rotation, your thumb will point the way of the resultant vector, and it should be pointing out of the page right now, or out of the screen at you. So using the right-hand rule that we discussed before, you could find the direction of this torque. All right, so learned a couple of things. The farther out the force acts, the stronger the torque, right? We can see that in the values of L here. Also physically we understand it. If we apply a force that's parallel or anti-parallel to the r vector, no torque. Also, a torque can cause different directions of rotation, counterclockwise and clockwise, and those are associated with positives and negative z-hats or resultant vectors. Z-hat only if it's an xy plane, it would be a different direction, but in or out of the board, effectively. Also, you can have forces that only have components that contribute to the net torque. So what if I had a force like this, F5, then I would have a component both parallel and perpendicular to the r vector, right? So this would be F5 parallel and F5 perpendicular to the r vector, because here's my r vector, right? This would be R5 now, points from the axis of rotation to the location of the force. And if I broke this vector up into two, clearly this one would not contribute, does nada, and this one does contribute. Is it a clockwise or counterclockwise rotation? All right, it's going to create a clockwise rotation. So it would be, if this is the y-x plane, it would be in the negative z-hat direction. Your thumb should be pointing into the board when you use the right-hand rule. So a lot of times when I think about the torque, I tend to just want to think about the part of the force that's perpendicular. So like if I wrote the magnitude of the torque vector out, I sometimes think about it as the magnitude of the r vector times F perpendicular, where I just pick out the perpendicular component of the forces and multiply them. Part of the way that I can do that as well is because if you remember, when we talk about the torque vector, when we talk about its magnitude, because remember the determinant gives us both the magnitude and the direction. We also have this other formula, right? And this is just for the magnitude of the torque. So we can know the magnitude of torque, but we would find the direction by using the right-hand rule. We could say it's clockwise or counterclockwise, right? Or we would use the determinant, right? Would be another method of finding the full vector magnitude and direction. Let's say we're only interested in the magnitude. Looking at the example that I just had of F5 over here, again saying it has a parallel and perpendicular direction to it. Here's my r vector. A lot of times I want to look at kind of the angle between the two. So if I had lined up my r vector and my force vector tail to tail, it would look more like this. And then this could be the angle between them right here, right? Angle between them. And this would be my vector broken up, so that would represent this component and this component here, and here would be the breaking up of the force vector. And this angle right here, we'll call it theta. Theta is equal to theta between minus pi over 2. And sine of the angle between the two vectors is equal to, well, let's solve for theta between, pi over 2 minus theta. This is effectively cosine of theta. That's that angle here, which is the same as this angle here, which is the same as this angle here. So this angle here is theta. And sine of the angle between is actually cosine of theta. And so if I rewrote torque as equal to the magnitude of R, I'd call that R5, magnitude of F, sine of the angle between them, this would be F5, sine of the angle between them. This would be F5. It would actually end up being cosine of theta. Again, theta is here, here, and here. And the cosine of theta component is given by this one right here. This is the sine of theta. So F5 cosine of theta is literally picking out this component. Here's my F5. Is literally, opposite of what I said. Is literally picking out this component, right? This is F5 cosine theta. Not this one, right? This one is F5 sine of theta. So if the magnitude of the torque is represented by R5 F5 cosine theta, this is effectively F perpendicular, right? I could have written the magnitude of the torque as R times F perpendicular, and really this would have been F perpendicular, and this would have been R5 right here, equal to F5 cosine theta in this case. So the magnitude is pretty much picking out the perpendicular component of the torque. The direction, of course, would have had to been given by me. R5 F5 cosine theta is the magnitude of the torque. It's in the counterclockwise direction, or the negative z hat, and that would give me the torque by that F5 force. Only picking out the perpendicular component and multiplying them. Counterclockwise direction, negative z. Okay, we've been playing around a little bit now, so let's do some examples and just quickly find the net torque acting on an object. So let's see what I'm going to do for you here. Oh, first, let me show you a video about torques.
Anything that can cause a rigid body to undergo an angular acceleration is called a torque, tau. Consider a pivoting mechanism with a device mounted on it that can apply a constant force in whatever direction we choose. When the angle between the radius vector and the force applied by the device is 90 degrees, the mechanism accelerates relatively rapidly. When the thrust is parallel to r, the angular acceleration is essentially zero. At an intermediate angle, the angular acceleration is between these two extremes. Repeatedly changing the angle of the applied force with respect to the radius vector reveals that torque varies with the sine of the angle. Decreasing the distance from the axis at which the force is applied decreases the angular acceleration and therefore the torque. Tau equals RF sine theta.
Okay, great. Okay, so general little overview of torque. Let's kind of just keep with my example, except for instead of a wrench, let's just say we have a rod. It's a uniform rod of mass m and length L, and it's fixed to rotate around this left-hand side on its end. That's the axis of rotation, is kind of coming out of the board at you right now. you're going to apply two forces on this rod. One of them is actually going to be acting right here at the center of mass of the rod, and we're going to call it gravity. So we're going to assume that this is the positive y hat direction, positive x hat direction, and minus mg y hat is the force acting on the rod right here at the center of mass location. And in addition to that force, there's going to be another force at this angle of theta. I'm just going to call it F. And F has just a magnitude of F. Okay, and we'll assume everything here is known. Theta, F, M, L, and of course G. So let's just find the net torque acting on the system. Okay, the system here is the rod. Now, this force of this rod, I feel like I should tell you, has been pinned down here at the axes. So there is a force acting there. There's a pinning force acting there. And a lot of times, like, that's not told to you. Actually, a lot of times it's not told to you that gravity is acting on the object, and that the fact that there's some kind of pinning force acting at the axis of rotation. But you know there would have to be. If I took a rod, I'd have to pin it there to force it to rotate. It just doesn't do it on its own. And this would be like a pushing force that somebody's counteracting gravity with, effectively. So I'm going to draw in this pinning force here. Excuse me. I'm going to draw in that pinning force there. But I don't know too much about it except for where it acts. I'm going to call it P. And I'm going to say that I actually don't know the direction that it acts in. You know, a lot of that has to do with, like, if you actually pin something. So let's say my rod kind of looks like this more. And this is where I've placed my pin, right here. I don't actually necessarily know the direction of the pinning force because due to other forces acting on the system, it could be resting, the pin could be resting right here, and then the pinning force might look like that. Or actually it could be resting over here, and then the pinning force would be pushing this way. It could be like this, and the pinning force pointing this way. It just kind of depends. You have all these degrees of freedom where the rod could rest. You know, if you're pulling down on it this way, there's a force pointing that way. That's the pinning force that's acting on the system. It can be a little bit complicated. And we'll talk about this a little bit more when we talk about equilibrium forces. But the idea is that I don't necessarily know the direction of a pinning force because of this circular nature. It could has infinite ways that it could point. Okay, infinite. All right, so let's say there's some kind of pinning force there, and I want to find the sum of torques acting on the system. My system is the rod, and the idea is if torques are given by R cross F, for every single force, there is a torque. So I look at my system, I say how many forces act on it? Well, there's 3. Great, then there's 3 total torques possible. Some of them could be 0, some of them may not contribute fully. But when I talk about the sum of torques, I'll have a torque for every single force acting on my system, and if I need to get rid of one, I will. So for instance, this is the torque for the pinning force, torque for gravity, and torque for force F, just like that. Okay. So let's take a look at each one of them. Let's start with the pinning force. I'm going to first just think about the magnitude. I don't know much about the direction of the pinning force, which is a bummer, but I do know something about its magnitude. So first I want to kind of say, well, what is the R vector for the pinning force? Here's the axis of rotation, and remember R points from the axis of rotation to the place where the force acts. So there it is, there's the R vector. It doesn't point anywhere. It's 0. You know, for gravity, the R vector looks like this. And for this force that acts all the way at the very end, the force looks like that. But the P force, The r vector of the p force is 0 in the x hat, 0 in the y hat, 0 in the z hat. It's just 0 vector. And so the magnitude of this thing is 0. So the torque for the pinning force, right, is just going to be equal to 0. And this is true for any force that acts at the axis of rotation. So 0. And why? Because its r is 0. So in my net torques, this one doesn't contribute, but let's look at gravity and force F. So let's find the torque from gravity. Let's find its direction, or I'm sorry, its magnitude first. It would be the magnitude of the r vector. So let's draw its r vector right now. Let me get a different color in here for r's. Here's the r vector for the gravity, right here, r sub g. So we'll call this little guy r sub g. And down here, I'll actually write out its full vector. It's L over 2 in the x hat direction, plus 0 in the y, plus 0 in the z at this current moment. So the magnitude of it, of course, is just going to be L over 2. I know it's at the halfway point because it's acting at the center of mass, and this is a uniform rod. Gravity, the magnitude of the force of gravity, right? That's just m times g. And let's look at the sine of the angle between them. What's the angle between them? Well, here's r sub g, here's minus mgy hat. The idea is that we line them up tail to tail, r sub g minus mgy hat. And the angle between them, matching them tail to tail, is 90. Sine of 90 degrees, of course, is 1. So this is again telling you that the perpendicular components contribute. And in total, the magnitude of the torque here is L over 2 times mg. Okay. What is its direction, you say? Well, you say, does this force cause a clockwise or counterclockwise rotation? And you'd say, it causes a clockwise rotation, which means in this case, since I'm in the YZ plane, this is going to be in the negative Z hat. And so the total torque is minus L over 2 mg Z hat. This is the torque from gravity. Now, I could have done this by taking the determinant. I have r sub g, and the force of gravity is equal to minus mgy hat. If I look at the determinant, the torque of gravity would take this form. Only has an x component, 0, 0. Only has a y component, 0, 0. Everything is 0 except for the z hat. You can prove that to yourself, but it gives me the same result. Okay, great. That leaves just F force on the end. So here is here's my rod again, and this is the F force acting on it at angle theta. If I was going to draw my R vector, here it is. This is the R vector for F. And so when I go to find the torque acting on F, I would start just by finding the magnitude and then direction. I would say this is the magnitude of R sub F times the magnitude of F times the sine of the angle between the two vectors. Well, the magnitude of R sub F, you can see R sub F is just positive Lx hat. And so what goes in here is just L, that's its magnitude. We already know the magnitude of F is just F, And so I would need to find the angle between r sub f and f, and I do that by matching them up tail to tail, like this. And this is the angle between the two vectors. And so looking at this quantity, the angle between it, is going to be equal to pi minus this angle theta that's given. And so in total, the magnitude of the torque acting on F is LF sine of pi minus theta. And sine of pi minus theta turns out is just equal to sine of theta. Just check that really quickly on Mathematica. So the magnitude of this thing, is just LF sine theta. Okay. Direction. Well, you would look at this and say, does this force give a clockwise or counterclockwise direction? And then you'd say, oh, it's counterclockwise. So that's going to be in the positive direction. And since I'm in the YZ plane, positive is out of the board, is the positive Z hat. And so the torque should be LF sine theta positive Z hat. Let me see if this makes sense. In particular, let me see if this makes sense, because I told you I can always write torque as RF perpendicular. That was easy for gravity because all of the force was perpendicular. But torque is RF perpendicular. Well, if the F vector is like this, here's angle theta, I could have represented it with an F sine theta and an F cos theta, just like this. And then here's my axis of rotation, here's my R vector. Then I would be only interested, and this would be the perpendicular component of the force, which would be this one right here, F sine of theta. So actually, in fact, I am right. The magnitude of this force was RF perpendicular is LF sine theta. So spot on that I can represent it as RF perpendicular. I don't necessarily have to go through the whole finding the angle between it. I could have just broken up the vector, found the perpendicular component, and wrote that in. Good to know. I also could have written this thing as a full force vector, like F. Sorry, guys. F vector has a component, right? Clearly, we've seen it in the positive y hat and negative x hat. So F as a vector can be written as minus F cosine theta x hat plus F sine theta y hat. That combined with R sub F being equal to positive Lx hat, we could have looked at the determinant. R would have been L, 0, 0. F would have been minus F cos theta, F sine theta, 0. And this would have been equal to, actually would have been 0 in the x hat, minus y hat, 0 also, plus z hat, L f sine theta minus 0 times minus f cos theta. So this would have been L f L sine theta z hat as well, coming out of the determinant. So I don't know how comfortable you guys are with that stuff, but sometimes that's easier to do. Well, anyhow, going back to the net torque acting on the system, remember we had the torque from the pinning force plus the torque from gravity plus the torque from F. And so remember we found this to be 0. So to find the net torque acting on the system, we would then be saying, well, what was the torque from gravity? And that was minus mg L over 2 z hat. plus the torque from the F force plus LF sine theta z hat. Of course, I could have included a plus 0. Maybe I should have. There we go. For the pinning force, that act where R equals to 0. And that's the net torque acting on that rod. A next step would have been then to apply Newton's second law to this, that says sum of torques equals to I alpha. And say, what is alpha? And the answer to that actually wouldn't have been too hard, because we already know the moment of inertia. We know the moment of inertia of a rod of mass m and length L that rotates about its end. We found the moment of inertia to be 1/3 ml squared. And so to move forward and to treat Newton's second law for rotation, which is effectively force equals ma, except for sum of torques, rotational force equals I, rotational mass times alpha, rotational acceleration. I could have solved for the acceleration of the system, would have just been sum of torques divided by I, where this is the I of the rod around its end. And so alpha would have been minus mgl over 2 z hat plus lf sine theta z hat divided by 1/3 ml squared. You know, that would have given me alpha. It's at this time that I would want to kind of simplify that numerator a little bit. Let me do that. And, you know, let me go ahead and pull out an L out of both of these quantities. And I'm going to multiply both the numerator and denominator by a 2 and a 3. Like, what have you, I know. So, in fact, this would have been minus 3 mg plus 6 f sine theta divided by 2 ml z hat is alpha. And I would go ahead and square this off now, but I would also want to think about, when would alpha be in the positive z hat? What does that mean? And when alpha is in the negative z hat? So when alpha is in the positive z hat, that's associated with, again, the counterclockwise direction for alpha. That means that the acceleration is counterclockwise when it's in the positive z hat. This means that even though my omega might be this way, that it's getting slower, omega is going down, and alpha would be then, until eventually it comes to a stop and forces it to rotate it this way. So alpha, the angular acceleration, is changing omega this way. It's either speeding up in the counterclockwise or slowing it down in the clockwise and eventually forcing it to go counterclockwise. If alpha is in the negative z hat, then the acceleration is clockwise, right? And so if you're moving already in the omega's moving in this way, then omega is just speeding up in the clockwise direction. There's acceleration. Or if it was initially moving counterclockwise, omega would be slowing down, coming to rest, and then changing its direction. And we can look at when alpha is equal to 0, means there is no acceleration. And that happens when 3mg equals 6f sine theta. So clearly, if 3mg is larger then 6F sine theta, then alpha is negative. If 6F sine theta is larger than 3mg, then alpha is positive, the pointing. And so that's how we understand what's happening with alpha. All right, I spent a much longer time on this than I expected. Next time when we meet, we're going to work some more sum of torques equals I alpha problems. And we're going to combine it with a Newton's law analysis, sum of forces equals MA, and then we'll start energy. All right, look forward to talking to you guys soon. Bye.